Hello, good morning, afternoon, good evening. This is the beginning of session 356 of Tesos and Wi-Fi. This one is part of the free class that we have in Wi-Fi design, the Wireless LAN Professionals Wi-Fi design class. We're going to be using all of the tools that we have available. We're going to be using Ekahau, Cedos, Hamina, Wavelify, and we're going to be covering a lot of stuff we don't cover in the regular class. If you're new or you are listening or watching us for the first time, you can go to the wi5ofthings.com. That's the website where we upload all of these sessions. In there, yes, it's mostly in Español, in Spanish, but if you click on the WLANPros Wi-Fi design class link, that's going to have a summary of all of the other sessions we've had. This is the same Wi-Fi class we've delivered to thousands of professionals worldwide. And in here, this is a combination of CWNA covering all the Wi-Fi basics or fundamentals, starting with regulatory domains, talking about the organizations that make Wi-Fi possible. Then we had a session on RF, just talking about amplitude, frequencies, antennas. We had another session talking about network interface controllers, NICs. How is it that they work? How is it that a Wi-Fi NIC works? Then there's been another session on the contention process. How is it that devices can access the medium, contend to access the medium? And then I think one of the last ones we had was on modulations, the modulation we use in Wi-Fi, all that stuff about QAM and BPSK and QPSK, all that is covered in that video. And the last one we had, that must have been back in May. Man, we've been gone for a while. We talked about dB math. In Wi-Fi, we use dBms to talk about power, dBis to talk about antenna gains. We talk about dBs when we refer to signal to noise ratio. And so in that video, we explain all that. Today, we're going to be talking about channels. There we go. Let me make this. There we go. And today is Saturday, July 25th, 2026. Again, this is the Wireless LAN Professional Wi-Fi Design class. We're just recording it as we can. We do a live class. Thank you guys for coming. I know it's Saturday. You're probably on your day off, but we're going to have this recorded for those who could not attend. Thanks for coming. Is audio, video okay? You heard me okay? See me okay? All right.
Yeah, I can hear you okay.
Sweet. All right. Well, today, July 25th, it's my birthday, and I decided to celebrate it doing what I like to do best, just sharing the little I know about Wi-Fi with you guys all over the world. So, canales, channels. Let's talk about channels and spectrum. How is it that in Wi-Fi, channels are distributed, assigned, used? Let's see if we can learn about this today. Remember that all of the vast majority of the frames in the air are small, okay? And the majority of them are not data frames. There's a lot of management frames, a lot of control frames, frames that are there to manage connections, all the association requests, response, beacons, probe requests, probe responses. All of those are management frames. They're there to manage connections, disconnections to a medium. Then there's control frames. There's lots of control frames. Anything that is there to control the traffic. That's what the control frames do. They control traffic. When you send data, you receive an ACK. That acknowledgement, that little frame, that's a control frame. It's there to control traffic, let you know that the delivery was successful. There are block ACKs, request and block ACKs. That's when I send data. And instead, because that's more efficient, instead of saying data ACK, I just send data, and then I send a block ACK at the end saying, hey, I sent you 100 frames. Which ones did you get? Then it's going to reply saying, hey, I got them all except, 90, 91, and 96. So I just resend those. That's to make the medium more efficient. So if most of the frames are not data, and most of the frames in Wi-Fi are small, less than 1,024 bytes, why do we need this big, huge channel? Well, we start with a 20 megahertz wide channel. This is the spectrogram of, this is the graph, basically the shape of an OFDM transmission. This is a 20 megahertz wide channel seen with the eyes of a spectrum analyzer. And 20 megahertz wide channel, when we talk about a 20 megahertz wide channel in Wi-Fi, this is how it's configured. We distribute, well, we don't do it, the protocol does it. You know, all the engineers that have worked on this, that this is configured. That 20 megahertz wide channel is divided in 64 subcarriers, baby channels, smaller channels of 312.5 kilohertz. Not all of them are used to send waves. Remember, we started talking about waves on session 1. We are going to send waves to represent ones and zeros. We saw that on the modulation session. On each one of these subcarriers, basically, that's a baby channel, and we're sending waves in those subcarriers. Then we are going to send data on the ones that are blue. The red ones are not used, and the green ones are pilot subcarriers. So subcarriers is another word for, you know, a smaller channel, a baby channel. So we're sending waves that are orthogonal, and that's what this is, OFDM, orthogonal frequency division multiplexing. Let me grab my pen and write up here. This is the shape of an OFDM transmission. OFDM. Subdivide a 20 megahertz wide channel, 64 subcarriers, 52 of those are used for data. Some others are used for, just mark this in red, as null subcarriers. The red ones don't carry any data. And then notice there is a dead subcarrier here in the middle to show where the center frequency is. That's why there is this dip in here, just to kind of like show that is the center of the frequency. 64 subcarriers, that's a 20 megahertz wide channel, and we're sending ones and zeros. We're sending waves in all of those data subcarriers. So that's a 20 megahertz wide channel. In OFDM, when a device has contended for the medium and has made sure that nobody else is sending waves, has made sure that there is no energy in the channel, has looked at the NAV, network allocation vector, and has weighted its ifs, and it has pulled a random number, the random back off, and counted down to 0. And when all of those conditions meet, then it will use the entirety of the 20 megahertz wide channel. One device talks at a time, which that is pretty wasteful, if you would say, because it's not very efficient. They just put it that way. When we talk to people that come from the cellular side of things, they say, what? Only one device talks at a time? That's stupid. Because in cellular networks, you can have hundreds of phones, cell phones connected to a tower, and then they're all talking at the same time in conversations at the same time, because they use a frequency division multiplexing or time division multiplexing. They subdivide the frequencies and assign chunks of frequency to people, devices, and chunks of time, and assign, just play with time and frequency in a way that you can subdivide a channel and allow multiple people to transmit at a time. That's more efficient. In Wi-Fi, OFDM works this way. One device transmits at a time. If the purple client needs to transmit, it waits for its turn, goes through a contention process that we covered in previous session, and then when it's its turn, it uses the entire 20 megahertz wave channel. And then the yellow device needs to transmit. Then it has to wait for its turn, make sure nobody else is talking. There's no energy in the channel. It make sure NAVs has counted down to 0. It waits on ifs, it pulls a random number, counts down to 0, and when all of those conditions meet, then it's the turn of the yellow device, and then it uses the entire 20 megahertz wide channel. That's how FDM works. So Wi-Fi, they say, like, how can we make Wi-Fi more efficient? Because if we look at 2.4, we have 3 channels. 1, 6, and 11. I know in Europe you have, we have 4. We have 1, 5, 9, and 13. Okay, that's okay. But then the recommendation is to just have 1, 6, and 11. This is why. If we have, just bring this guy up here. There we go. If we have a 20 megahertz wide channel, let me just probably use this color here. I don't know if that color is very, let me use a different one. How about we use blue? That better? So if that's the OFDM shape, then that is a 20 megahertz wide channel. If this is an OFDM shape, that is the shape of an OFDM transmission, that's another 20 megahertz wide channel. And if we, let's use black, why not? If we have this and other OFDM shape, that is another 20 megahertz wide channel. So these do not overlap. They're not interfering with each other on top of each other. If I, for instance, put this guy here on channel 9.
Ferney, sorry.
Dime, yeah, go ahead.
Yeah, sorry for stop you, but we don't see your screen on wire design.
What are you saying?
Just you.
Just
you are
me?
Beautiful, but just you.
I can see it. I can see it just fine.
Sorry.
Rafa, can you see it?
Yes, I can see you drawing it.
So, Mauro, maybe what happened is that you went to another window and then my screen is on the background somewhere here. Let me stop sharing.
Okay, sorry.
And let me share again, and then it's going to put it on the front of your screen.
Okay, now I will see. I don't know.
See what happens when you get distracted?
Yeah, I see now.
Okay.
Sorry.
All right. No, not a problem. Thanks for letting me know. So if I have this guy on channel 9, those subcarriers, as we just described before, see, this guy, this subcarrier has energy on those channels, okay? So if we have another AP on channel 9, then it's going to be interfering with this guy here, and it's going to be interfering with this guy in here. So it's basically interfering with those other guys. If we have another access point, let's say on channel 3 over here, okay, this guy is going to be interfering with this guy on channel 6 and this guy on channel 1. So they're going to be on top of each other. They're overlapping, they're interfering with each other. This is why the recommendation of having channels 1, 6, and 11. Not, I know Ruckus and many companies, they just set up their APs to find the best channel, and they put 1 through 11. And then some APs land on channel 3, on channel 7, on channel 9. That's bad because we want to just have clean, simple RF. What happens is, this is what 2.4 looks like in most environments. There are APs on channel 1, there are APs on channel 5 or 4, that'll be like 5. There's APs on all kind of channels. So this is a really congested environment. So the spectral mask, that shape that we just talked about, is going to look like this. That's an OFDM transmission, okay? If we move then to 5 gigahertz, in 5 gigahertz, we have more channels. They said, you know what? This is working out pretty good with the Wi-Fi, but how can we have more channels? This is when we had 5 gig at the beginning, we received this Uni 1 channel. Let me just make those green, as green is in here. So these green channels, okay, Uni 1 and Uni 3. Uni stands for Unlicensed National Information Infrastructure, Uni. They say, okay, we can use, because here's what happened. At the beginning, let me stop this so that I can delete all this stuff. How do I, hang on. Okay, if I go back to this guy. They said, what are we going to do with this Wi-Fi stuff? Let's going to assign channels that in most regulatory domains in the US, in Colombia, in Italy, in Sweden, everywhere, 2.4 is a frequency that has been assigned, and they told all of these manufacturers, basically, if you're going to create a device that is going to be used for industrial, scientific, or medical purposes, go ahead. Use the 2.4 band. You don't need a special permit from the government. You don't need anything special. Just create devices and make sure that you obey our, rules. The power you can use, the channels, the energy, you can use the type of antenna. So every regulatory domain, we covered that like on day one of these classes. Then these are called ISM bands, industrial, scientific, and medical. So this is why in 2.4, yes, we have 3 channels for Wi-Fi, but let's say General Electric, they say like, oh, so I can create a device with a magnetron, put it inside a metal box, and then it generates waves in 2.4 band at 2.4 billion cycles per second. And then at high power, they will excite the particles in your food. They'll heat it up. That's what a microwave oven is. It's a device that generates waves, same as we do in Wi-Fi, at 2.4 billion cycles per second, and then it heats the food. Then there's other technologies. There are other technologies that use 2.4, like Zigbee. They have different channels, different channel widths, different methods to access the medium. There is a BLE, Bluetooth Low Energy. It has these 3 advertisement channels, channel 37, 38, and 39. And then that's where they're always advertising stuff. And Bluetooth. Here, Bluetooth, it has 79 1 megahertz wide channel. Is it 79 on 80, Martin? 79, well, from 0 through 79, right? Let me just, I don't have my glasses with me. Let me get my glasses because I'm having a hard time saying this. Hang on. Okay. Yeah, so it's 80 channels from 0 to 79. That's small here, but I can see it now. Oh, 79. So we have 79 channels, and what Bluetooth does, it does frequency hopping. Once we get to spectrum analysis later in this class, we will have the spectrum view of how Bluetooth looks in the spectrum. So yes, 2.4 gets congested because there are wireless cameras, other technologies that also use 2.4. So we have to share the medium with them. We have different channel widths. We have different ways to access the medium. We try then to avoid transmitting with their other devices transmitting, but we try to maintain our Wi-Fi channels clean. So 2.4 gets congested. This is the, just make another one in here. This is just a simple view of how the 2.4 spectrum is allocated. We have not just Wi-Fi, so this is not exclusive for Wi-Fi. Many other devices, many other technologies use the 2.4 band. That's why it's congested. There are only 3 channels. It gets busy. And here's where 5 gig comes to save the day. Because we have now 20 megahertz wide channels. We have 25 of these guys right here. So you're going to have 20 megahertz wide channels all the way across. Initially, we got Uni 1 channels and we got Uni 3 channels. Well, actually 165 was not part of that. At the beginning, we got up to here, and then this channel 165, they made it available. And they say, well, and that's going to be an ISM band. That's when we had those wireless phones. They say, oh, this is a 5 gig phone, so it doesn't interfere, you know, and gets too much interference in 2.4. That used to be an ISM band. But then I don't remember when it was 2014 or so, long time ago, they joined and they made this a Uni 3 channel. So those are the ones we got originally. So the blue channels, the ones you see here in the middle, since this guy said like, hey, you know, this is working pretty good, this Wi-Fi, but why don't you give us more spectrum? Why don't you give us those channels there in blue? Because look, they're like sandwiched in between Uni 1 and Uni 3. And they say like, no, those channels are not for Wi-Fi. They already belong to somebody. Some entities, some organizations already use them. They're used for radars, for radar systems, for a maritime radar. They are used for airplane radar, for weather radar. This is the terminal Doppler weather radar system. Those 3 channels, 120, 124, and 128, they are not allowed in many places. Like Canada did not allow those. They allow them now. Okay. But like in Australia, they are blocked. You cannot use those 3 channels for Wi-Fi because they are for the weather radar system. There are also many entities. So they basically say like, no, you're not going to use this for Wi-Fi. This is for radars. And they say like, but look, for instance, we live in Utah. We're in the middle of the desert. We don't have any rivers around here. We don't have any harbors. We're not near the ocean. We don't use those maritime radars. So, well, but there are airplane radars and terminal Doppler weather radar systems. So, well, why don't we do this? If you let us use these channels for Wi-Fi, we promise that, let's say if I'm on channel 100, if I have an access point in channel 100, and then I detect energy from one of those radar systems that you say you have, then I will dynamically select a different frequency and I will move. So those channels in blue right there are called dynamic frequency selection channels. The way this works is if an access point detects energy in one of those channels, then it will dynamically select a different frequency and it will move. I have a presentation that I did, I don't know, a few years ago. Let me just probably post the link in here. And let me move this guy around. And now, hard time moving this window out of this screen. Hang on, Mauro. We'll get it out. We'll get it out. Here, I'll put it right here on this side. How's that? And then if you make a search, let me just make a search here for Fernet Nos channel switch announcement. There's a presentation. Let me just pause. That I did at the Wireless LAN Professional Conference. Let me copy this link to the chat. I'll post it in there. Where is the chat? Come on, chat. Where is my chat? Oh, here we go. Hang on 1 second. Bear with me. Okay, in the chat. Oh, I just opened the chat. Let me, there you go. I just pasted this video there. You can watch it later. I don't have to watch it now. But then I talk about the channel switch announcements. And this is a test I did where I put a radar signal in access points that were on this DFS channel. And then we notice how the APs move. They move to different channels. Some moved to channel 40, they went down. Some others went up. Some others changed channel width, went from an 80 megahertz wide channel to a 20 megahertz wide channel. This is what happens. You generate a radar signal, and then it will cause the APs to move. All right, let me just come back here then. Now, there we go. So these are the DFS channels. Now, does that mean that if you are designing Wi-Fi near an airport or near a harbor, does that mean you cannot use Wi-Fi on this channel? Like, no. Use DFS channels until you can. If the access points detect radar systems, they have DFS events will be reported in their logs, and then they will just move. Then they're going to record a DFS event in your controllers. And you say like AP that was in channel 100 with MAC address ABCD has moved now to channel 36 or channel 40 or whatever channel it moved to. And there is a whole bunch of rules for DFS. David Coleman did a very good presentation about DFS channels. Just move this guy here to the side again. And then let's look for David. Come, I also post. I will post. Let's see. This one. Is this the one? Yeah, this will work. That's a longer one. And here he spends just time explaining about DFS and in more detail how it works and the regulations you have to, like when you move to a different channel, if it's a DFS channel, you have to wait 60 seconds there just listening to make sure there are no radar signals in it. So there's another video worth watching. Let me just also in the chat paste this link. Let's place that right there. And then you can watch that later. Okay, let's continue over here. DFS channels. And let's talk about channel widths as well. We have 20 megahertz wide channels. That's great. But then with 802.11n, one of the improvements or the things that they introduced, yes, they added MIMO, they added short-guard enable, they added a whole bunch of improvements to the standard. And then they also said, like, how can we make this Wi-Fi thing better, faster? How can we go faster, Mauro? And they said, well, you know, you have a 20 megahertz wide channel. What if we bind two 20 megahertz wide channels and we create a 40 megahertz wide channel? Then we're going to have more subcarriers to send more waves at the same time, so we can go faster. So if we create 40 megahertz wide channels, that sounds good, huh, Mauro? You can go faster, you have more subcarriers, you can send more waves. That's great, but here's the problem. When you create a 40 megahertz wide channel, that's actually not a 40, that's two 20s put together. That's what's called channel bonding. I have two channels put together, which means that now I have less channel. Because if I go across, I only will have, let me just use this color, I will only have 12 40 megahertz wide channels. So even though it sounds good that you can go faster, then the problem is that you're going to have less channels. So if you have, let's say, a place with 30 access points, an office, 30 access points, and they see each other. So if you use 40 megahertz wide channels, then you have 12 channels. So you assign the first 12 APs 40 megahertz wide channels. Where are you going to place AP number 13? Well, you're going to have to use one of the 12, then you're going to have to repeat, okay? Once you have APs in the same channel, they're sharing that channel, and that's what's called co-channel interference. And I know Peter Mackenzie now is fighting over like, no, it's called co-channel contention, CCC, not CCI. But it's interference. You have other devices basically, yes, sharing the medium. Yeah, that's co-channel contention or co-channel interference. It's in documents everywhere. We've been taught that for years, for decades, that it's called co-channel interference when you have two APs on the same channel. Because remember, Mauro, only one device transmits at a time. If you have two APs in the same channel, they're sharing that channel. And if you have one AP with 10 devices, and you have another AP with 10 devices, and both are in channel 36, for instance, then now we have 22 devices in the same channel, because the AP is just another radio that needs access to medium. So APs are not special. I mean, they're special, but when it comes to accessing the medium to send waves, the AP has to make sure that nobody else is talking, that there's no energy in the channel, that nav has counted down to 0, that it waits an if, that it pulls a random number, that counts to 0, and when it's its turn, then it transmits. Okay? Not very efficient, huh? But that's how Wi-Fi works. So if we want to go faster, 802.11ac, they say like, we can join 240s or 420s together and create an 80 megahertz wide channel. So if we create an 80 megahertz wide channel, now we can go faster, Mauro, because we're putting 420s together, and then we have all of these subcarriers, and when it's my turn, that's when they say like, yeah, you can send 1.3 gigabits per second. Yeah, if you have an 80 megahertz wide channel and you're this close from the AP and you're the only one using the spectrum. So, but yes, 80 megahertz wide channels will give you more throughput. And vendors like it because, hey, a wider the channel, if you have a bake-off, a competition with other vendors, then the wider the channel, the bigger the number. We have talked about, and we will talk more about this speed test stuff. People love that, and this harmful. Speed test is bad for your network because every time you're doing speed test, you're going to go as fast and put a whole bunch of packets in the air. There's another presentation I have out there where I talk about speed test and how bad it is for your network. So I should just put it here in the chat also. Those who are talking about channels, yeah, the wider the channel, the more subcarriers you have, the more data you're sending, the more throughput you get. Let me just, how is that presentation called? Throughput analysis? I don't even know what it's called. Analysis, Ferney Munoz. Throughput testing and active survey. Yeah, I did that in February. And here I explain how when you're doing speed test, let me just bring this guy back up in here. Let me move this guy back. See, the channel utilization is really low on a Zoom meeting. And right there during that session, I started a speed test session and my channel utilization went to 93%. It utilizes the channel heavily and it puts a lot of packets. And yes, the wider the channel, the higher the throughput because you're sending more. But let me just put this in the chat as well. And okay, let's come back here. So with every megahertz wide channel, we can go faster. But what's the problem? That we're only gonna have 6 channels to use. That's it. So we go back to that same example of having an office, open space, or a warehouse, and you are using 80 megahertz wide channels, then you have 6 channels. So the first 6 APs get a channel, really wide. And then where are you going to place AP number 7? Well, since you only have 6 channels, you're going to have to repeat and then assign the same channel to AP7. And then once you get to AP13, where are you going to place it? You already use all the 6 channels twice. Then you're going to have to reuse one of those channels. Let's say channel 36 at 80. then now you have 3 APs on the same channel. If they see each other, if they hear each other, then they're sharing the channel. Okay. Now, where are you going to place the next AP? See the problem, Mauro? It's just, you know, the more APs you have and the less channels you have, the more times you're going to have to reuse those channels. And they're on the same channel. They're sharing the channel. So you're making it slower for everybody because everybody has to wait for their turn to send waves. Questions or comments up to this point? Okay.
I put some comments in the chat about Unit 2A.
Okay. Oh, in the chat, yeah. About
You were a little bit
DFS.
fast.
Oh, perfect. Yeah, I'll leave that in the notes.
Faster. You were a little bit faster saying DFS was
Yes.
new. That was new. So that when they open up 2E, they also included DFS on 2A. 2A was free from DFS from the beginning. Okay.
It was, huh?
Yeah.
All right.
That changed.
Yeah.
And then it changed 2014, which is interesting. Which says that Ubiquiti was one of those companies that had the possibility to turn off DFS detection, and the FCC decided we will ban that because that caused something very, very bad happening in Puerto Rico.
Yeah, and what had happened was that, let me just tell you a story, kind of in line with what Martin is bringing up. Happened that many years ago, a company called Ubiquiti, they make these point-to-point links. Now they're doing a lot of stuff in the enterprise and doing a lot of things. But we've known Ubiquiti for doing these really good, inexpensive, low-price point-to-point links. Happened that they had sold these point-to-points for a WISP, a wireless internet service provider. So you have an antenna on the, let's say, the town, and then you have a wireless link to a village near the town that is too expensive to run wires. Then they put a point-to-point link, and then they sell internet to people. So what happened? Oh man, sorry, I'm joking. What happened was, what happened was that, let's say a technician goes and sets up that point-to-point link. Then comes an airplane. The AP detects weather radar or detects the radar system, and then that energy causes the AP to move. Let's say you have it in channel 120, and then this antenna detects the energy, and then what's the promise? I will dynamically select a different frequency, and it moves. So what happens to that link? Let's say this radio moves to channel 36. Now that link goes down. So there's no link. People say, hey, the internet is down. They call the company. The ISP sends a technician. Without knowing how DFS works, they say like, this is so weird. I put this link in channel 120, and now this antenna is in channel 36. The link went down. Let me put it back on channel 120, reestablishes the link. It works now. Does it work? Yeah, it works. Okay, good. Then the guy leaves. Comes another airplane. Detects energy, radar. Then it moves to channel 48. The links go down. Then they just kept going. So at the time, instead of just saying like, yeah, we cannot do this, they say like, oh, let's allow people to just disable this. And they added a button, I don't know, it said something like obey regulatory domain, yes or no. And then people, the technicians are like, oh, you know that problem we were having that the link will go down because the APs will switch channels? This button, if you say obey regulatory domain, if you remove that check, so don't obey it, then it stays there. It doesn't move. And then the links stayed up. And they started spreading that in the forums, but then some military bases started noticing that airplanes had detected wind shear event. There is wind that's dangerous for the airplane to land. They would ask permission to land at a different military base. So they start saying like, look, there's weather events. It's like, yeah, but there are no weather events. There's no wind. There's no weather. Something is jamming the radar. So they got the FCC involved. They went, and of course, this is like the short of the story. It's getting more complicated than that. But then what they did is they sent the FCC, they checked and made sure that everything was well, but then they found these Wi-Fi point-to-point links that were staying on DFS channels and not moving. So they basically removed these 3 channels from Wi-Fi for many years. They gave it back to us. And then, I think that's in 2014 when we got them back. Okay, we had them gone for a while, but we received them back in the US, and they basically punished the entire industry. They said like, why don't you just punish Ubiquiti? And they say like, no, we're going to send a message to the entire industry that if anybody violates this rule of DFS channel, then we're going to get punished and get fined. So you're going to get thousands, hundreds of thousands of dollars in fines. So DFS we can use, but if there are DFS events and the APs move, then maybe in that area you are not supposed to use certain channels. If we're using 160 megahertz wide channels, it's not 160, it's 8 of these guys put together. I saw a place where they were complaining that the Wi-Fi was low. I go do a survey, but even before I did the survey, I realized that they were using 160 megahertz wide channels, which means you are using all of that spectrum. And all of the APs were on one channel because they had like 14 or 16 access points in 160 megahertz wide channel. It was only one channel. You had everything on the same channel. So yes, that's why things were slow. So and then you're going to end up with just like two channels. You're just going to end up with 260 megahertz wide channels. So yeah, you don't want to use those 160. I know, and they keep talking about 320 megahertz wide channels to go fast and have big numbers, but in theory, it works in the enterprise. We won't be able to use those wide channels. 80s, if you can. If not, switch to 40s. And if you cannot use 40s because there's too much interference, then go down to 20 megahertz wide channels. That's what we did at this event, where we had like close to 300 access points, open space. Then they see each other, use the narrowest channel, 20 megahertz wide channel. Here's the other problem when you have wide channels. Not only you have less channels, but since you have, let me just go forward. If this is a 20, that's what a 40 is going to look like, okay? And this is what a 40 megahertz wide channel looks like in the spectrum. If you look at Adrian Granado's application, it's going to highlight, see if this is a 40, the channel with the stripe, that's the primary channel. The other one is a secondary. So all of the frames that are management and control will go on the primary. And if I have enough data to send and I need both 20s, then I'll use both 20s. If we talk about an 80 megahertz wide channel, this is what an 80 megahertz wide channel, because it's not an 80, it's 4 20s put together. So if we have an 80, this is what an 80 looks like. And then using Wi-Fi Explorer Pro, you're going to see that one of these channels is highlighted. It's got stripes, got lines in it. That is the primary channel. And then the other ones are secondary channels. And here's the problem. If you have an 80 megahertz wide channel, let's say this guy right here, then the OFDM is going to look something like that, the OFDM shape. If this is my primary in here, and these others are secondary channels, if I need to use the medium, how do I know if those other 20s are available? Then I'm going to send a type of control frame that is called an RTS CTS, request to send. So I basically send this little frame request to send on each one of those 20s. Request to send and request to send. I will receive a clear to send from devices in there, and the access point, let's say, is going to respond. Let's say 2 access points are here. I'm going to draw the other. And then if I receive CTS, clear to send, like go ahead and send CTS, 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 then I can use all 80s. But what happens, let's say, if in this same area, there is somebody else with a 40 megahertz wide channel, let's say right here. And let's say if this is channel 36, channel 40, channel 44, and channel 48. So the first one is channel 36 at 80. See, that's the blue one with this primary. Let's say this other guy is channel 48 at 40. And this is the primary. This is the secondary for the yellow guy. And let's say in this same place, there is a guy in channel 44 on a 20 megahertz wide channel. So that's basically its own primary. There's no primary or secondary, it's just primary because it's only one 20 megahertz wide channel. So this guy has this primary, this guy has this primary, and of course the blue has the primary. Those primaries don't match. Every time these devices need to send data when you have wider channel, then there's going to be RTS, CTS, which what it does is it increases the amount of control traffic, because instead of being data ACK, data ACK, data ACK, now it is RTS, CTS, data ACK. Basically, can I use the channel, or I'm going to be using the channel for 320 microseconds? Go ahead and use the channel for 320 microseconds. I send waves for 320 microseconds, and then I get an ACK. So I am increasing the amount of traffic in the air. Instead of being, Mom, I'm hungry, I'll give you food. Now it's, Mom, can I talk? Sure, son, go ahead. What do you have? I'm hungry. I'll give you food. So it's less efficient. We're adding more traffic to the air. This is a protection mechanism, just to protect and make sure that these other devices are not sending waves at the same time that you in your 80. But if the primaries are not in the same primary and they don't hear each other, then there is a high potential for increasing retries. Because if I send a frame and at the same time that I'm sending my frame on an 80, you send your frames on a 20 or on a 40 that happen to be on the same air, in the air it's just waves. So if you don't understand, if you don't get what you receive, then you don't confirm, you don't send an ACK to anybody. So basically, wider channels are good because they have more subcarriers and you can send more data. But when you have wider channels, then you're going to have more potential for interference and have devices on top of other devices. And if the primaries don't match, then that's what's called overlapping basic service sets. Overlapping basic service set. Because you have all of these channels on top of each other, and then you have more frames in the air, and then there's more problem, more contention, more interference. Questions or comments up to this point? Okay, today, session 356, we're talking about channels. Started with a 20 megahertz wide channel, then we moved to a 40, then we moved to an 80. This is what an 80 then is going to look like when you are doing a transmission, which is inefficient because only one device uses the entire medium. You compete for a transmit opportunity, and then when it's your, have that time for yourself, then you use all those 20 megahertz wide channels and all those subcarriers, and then you send data, and then you can have big numbers when you're doing throughput testing or when you're sending big files. Use 80s if you can. If you have an office with 5 access points, Well, you have 6 access points you could use. Then sure, you can use 80s and life is good. In your house, maybe 80s is good if you're not too congested by neighbors. If there are too many devices, then switch to 40s. If there is still interference, then switch to 20s. It's that simple. This is how real life looks. You have 20s and 40s and 80s all mixed up together. And in here, I don't even have a 160 megahertz wave channel, but then that would look something like this. And then that guy is going to have a primary, whatever primary it chooses. And then all the other ones are going to be secondaries and all these guys. This is OBSS everywhere, overlapping basic service set, because you have 20s and you have 40s and you have 80s all on top of each other. Questions up to this point? Access points that are in the same channel, like these guys in here, well, that's if they are in the same primary. Let's just use this color. See, this guy and this guy and this guy, if they are on the same channel and they have this as the primary and they are secondary, this is what called CCI, co-channel interference, because they are in the same channel. Adjacent channel interference is when you have, let's say, let's use this color. Let's say you have this guy over here and you have this guy over here. So they're adjacent to each other. Remember those OFDM shapes? They have like this skirt that goes on the side. That's energy. So these guys, if they're too close to each other, then there's potential for some interference because that energy is going to be seen by the other device. So maybe you're going to go to a lower modulation because it doesn't work. The ideal is to keep them separated. But the reality is for each frame that you're going to send, I like this graph. This, I think, is from Aruba. But what it shows is if you're sending a 3,000 byte frame, that's the payload right here. You're sending, maybe just use a different color so you can see where, there we go. If you are sending a 3,000 byte frame, it takes you about 360 microseconds to send it. If you're sending a 90 byte frame, just tiny, small payload, it takes you like 240 microseconds. Because of all the overhead, all of the other things that have to happen for the frame to gain access to a medium and all the time that you have to go through everything, then this is a graph that represents, you know, how busy the medium gets with overhead. So let's go back to this. Most of the frames in Wi-Fi are not data. They're just control and management frames. And the vast majority of these frames are tiny packets. So if most of the frames in the air are small, why would you need an 80 megahertz wide channel? Well, you don't. That's why Wi-Fi 6 comes to save the day. They say like, well, that's not efficient. How can we be as efficient as cell phones that they use time domain multiplexing and frequency division multiplexing? How can we do that? And say, well, how do they do it? And say, well, they use something called OFDMA. OFDMA, orthogonal frequency division multiple access. With OFDMA, what they do is they say like, well, we get a 20 megahertz wide channel. We not, see, because this is OFDM. This is how OFDM did it. It got the 20 megahertz wide channel and subdivided in 64 subcarriers. So, well, how can we make this more efficient? Well, let's do as OFDMA does, OFDMA. And then we subdivide it in 256 subcarriers. So smaller baby channels. And then what they do is they assign subcarriers resource units to different users, now allowing multiple devices to transmit at the same time. or the access point to transmit to multiple devices at the same time. And doing those divisions, you can have up to 9. You can have up to 9 resource units assigned, so you can have up to 9 devices talking at the same time on a 20 megahertz wide channel. This is more efficient because you're using the spectrum more efficiently. The way it's going to work then is that it's going to have more subcarriers. This is Wi-Fi 6 or 802.11ax. So with 802.11n, we went to 40 megahertz wide channels, putting 2 20s together. With 802.11ac, we went to 80 megahertz wide channel, putting 4 20s together. So back then, the idea was to go faster, wider, better, bigger, farther channel. And they said, but this is not working because now we have so many devices. And if we make these big fat channels, then we're not going to be able to have better distribution of the spectrum. We're going to have lots of interference. How can we go the other way? And with Wi-Fi 6 or 802.11ax, they said, like, instead of going wider, 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 why don't we go smaller, 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 and then give devices the opportunity to get smaller resource units assigned. And then that way we can have multiple devices talking at the same time in a way that it is the access point, same as in a cell phone network, that the tower is the one that controls who talks and who gets what spectrum based on what you need. So if I have reserved the airtime, let's say I'm the access point and I get a transmit opportunity. Within that transmit opportunity, I'm going to send a trigger frame. Hey guys, do you have anything to send? And let's say Martin comes back and sends me a frame and says, yeah, I got this much to send. Mauro, you come back and say, I got this much to send. Nick, you come and say, yeah, I got this much to send. And then Anton, you come back and say, yeah, I got this much to send. Then I will do a math, calculate and say, well, you know what, Martin, you get this much spectrum. Mauro, you get this much spectrum. Then Anton, you get this much spectrum. And then Nick, you get this much spectrum. When I say go, you guys transmit. That's what this is doing. It sends the trigger frame, okay? Then each device gets that assignment, sends the data, and then they get the ACK and confirm. And then you're going to have multiple devices transmitted at the same time. You're just assigning different chunks of the spectrum. This is a 20 megahertz wide channel, but it can be broken into different resource units and then have multiple devices either sending stuff to the AP or receiving stuff from the AP at the same time. It has to have Wi-Fi 6, 802.11ax access points, and 802.11ax clients. They have to have support the same standard, or else it's not going to work. Because people think that, oh yeah, now I can have multiple devices talking at the same time. But if you have 802.11a, 802.11g, 802.11n, 802.11ac devices, they're not going to be able to all talk at the same time. They go back to the rule that one device talks at a time. This is what Wi-Fi 6 or 802.11ax is. Questions or comments up to this point? You guys are so quiet.
All clear, Ferney.
All clear. Okay, good.
Yeah,
clear.
yeah. For me, it's so clear.
Clear as mud, huh? All right. Oh, we have a new visitor today, Mr. Google Pixel 7 Pro. Hey, welcome. What's your name? I think you're on mute. All right. Well, it looks like we got people from all over the place. Thanks for coming. We're 1 hour into it. We have Martin from Sweden, Andre from Russia. Where's Andre from?
Can I add a comment?
Yes.
I'm not sure. I didn't listen too carefully when you were talking about the OFDMA. But the slide you have here, that is, you have 4 clients that can talk at the same time. Most people don't realize that you only get 1/4 of the speed that you had before. a little bit because now you only have 1/4 of the channel width.
Yeah,
So
absolutely. And if you have more, but if the frames that are being sent are small, then the distribution of the channel makes it more efficient because you don't need the 80 or you don't need the 20 to send a small frame. So
you like transmit will take 4 times as long. So
yes,
just there's another kind of gains that you get from OFDMA, that you're reducing some overheads instead, not just speeding up the clients. Basically, doing that around.
absolutely. And I tried it. I think it was in Sweden where I first tried this at that. You probably remember in Stockholm. You most likely were there when we did the Wi-Fi meetup at that mall. What is it, Scandinavian?
Yeah.
And it didn't work. I tried it in the hotel with one AP, one client, and I couldn't make OFDMA to work. Like, oh, but I only have one client. It uses the entire thing all the time. And then during the event, I asked everybody, hey, who's got Wi-Fi devices? And at the time, several said, I got some. And then this is an access point, and this is, a trigger frame assigning 106 tones to a device, 52 tones to another device, and 52 tones to another device. It allocates that, and then using the different association identifiers, it's going to have 3 devices receiving data at the same time. And it just assigns and assigns different chunks of the spectrum. Okay. If we have then, because now with AC, they were talking about multi-user MIMO.
Can I just make another comment, which is
sure.
The AP constantly monitors if it should use OFDMA or not using OFDMA, falling back to OFDM. So there's an algorithm try to understand if it's more efficient to switch over to OFDMA or be back out OFDMA. And they can't do the same at both times. So sometimes the AP is doing OFDM, sometimes doing OFDMA, which means they had to do it constant calculation, which is the most beneficial. And that was what happened with you in Stockholm. You didn't have the system decided, sorry, there's no good OFDMA because we're not going to gain anything. It's better that you have the full channel yourself. So
yes.
This algorithm has been a little bit a problematic thing during the years, that not all vendors are doing this in the same fashion and triggering and switching over to AX and doing OFDMA. Instead, they are kind of say, okay, I don't care. And even if the clients can do that, their system may say, okay, I will not gain so much. I will constantly try to make it the best use of the channel. So it may go back and forth between OFDMA and OFDM on the decision which is the most efficient for my clients. And that's not an easy algorithm to create because there are so many variables involved. That's why some people are not seeing any benefits of OFDMA.
Yeah, and this is, again, as Martin specified, the AP is the orchestrator, basically one that controls this. Now, it's not only downlink from the AP to the client, it's also from the client to the AP. But again, it is the AP that starts with that buffer status report frame, basically asking client, hey, do you have anything to send? Or I have this to send you. So it works download, it works upload also from clients to APs if the environment and the devices and the vendor that is implementing it has the ability to do it. This is the perfect world. In 2.4, you have channels 1, 6, and 11, no interference. This is real life. Perfect world in 5 gig. You have not adjacent channels. See, everybody's got like they skip a channel, 20 megahertz wide, everybody's happy, and there's no interference, there's no co-channel interference. Perfect world with rainbows and unicorns in 5 gig. This is real life. Lots of interference, lots of APs, lots of CCI, lots of ACI, lots of OBSS. Here, before we move out of this, then CCI, that's when you have APs in the same channel. ACI, adjacent channel interference. When you have APs adjacent to other AP, like these two guys, see? These are causing each other adjacent channel interference. I don't know. Let's see if we can find some that are just CCI. Well, several. Well, these two. Assuming that these two are on both this primary channel 140, then this will be CCI. Those are co-channel interference. Those are APs in the same channel. And then this one here at the end is a good example of overlapping basic service set, because you have 20s and you have 40s and then you have 80s, all on top of each other, causing each other interference. 6 gig comes to save that day. With 6 gig, we have 59 20 megahertz wide channels. Okay, because they say like, 2.4 got crowded, then we got 5 gig, and it got crowded. We need more spectrum. We need more spectrum. Give us more spectrum. And then the US, we got, you know, the FCC to approve 1.2 gigahertz of spectrum. Gives us 59 20 megahertz wide channels. But then this is very similar to DFS. That's not yours. That belongs to somebody else. But what if we play nice and then we use it, and if then the owner comes, then we leave? So that's when AFC comes into play. 6 gigahertz is not as busy in certain areas. Okay, I think this is just my man cave here with a lot of stuff, and then you can have wider channels, and there's lots of spectrum. But here's the problem. Even though we get 59 channels and we got Uni 5, Uni 6, Uni 7, and Uni 8, and then they said, oh, 80s is the new 20s because you have so many channels. Yeah, we can have like 14, I believe, 14. Let's see, 4, 5, 3, 8, 10, 12. Yeah, 14. Sorry, I still count faster than Espanol and Spanish. 14 80 megahertz wide channels. They say like, wow, you can have just 80s everywhere. But here's the other problem. This is not universal. This is not harmonic. It's not like 6 gigahertz is available everywhere in the world. We started in the US, then the UK added some spectrum, not all of it, just like 500 megahertz. And then other countries started approving slowly. And look, this is just a few, okay? There are many other countries that have approved it. Some got it, and now they're trying to get it back. It's a constant fight because all the companies that buy and pay the government for, let's say, spectrum to sell point-to-point license links, they say like, why are you giving this for free to the Wi-Fi people? They're like, well, the benefits it brings to humanity and the technology. And said, yeah, but they're going to be causing interference to us. They're going to be generating all these signals for the Wi-Fi stuff, interfering with, you know, Earth to space satellite communications, all these astronomical observatories, all of these TV stations, radio stations. There are so many that pay for that spectrum, and then they say first responders are going to be affected. All the firefighters and police and all these other organizations that use this 6 gig spectrum are going to be affected. So they created something called AFCs, automatic frequency coordination. We'll talk briefly about it, but then 6 gigahertz brings more spectrum, more channels. But then there are other things that you would have to know about in here. There is, for instance, see these guys in black right there? Those are called preferred scanning channels, PSCs. I did another presentation about PSCs. Let me put that in the chat. So, see, you guys have homework, man. It took me a while to come back, but now you have homework. This work? Yeah, preferred scanning channels. This guy over here. In there, I explain why preferred scanning channels and why is the second one of each group of 80. And let me copy this link. Oh, they approved 6 gig in Chile, huh? But well, at least you were using all of it and now only the lower band. So you lost the upper band, Sebastian?
Yes, we lost in 2 years ago, 3 years ago.
Oh, and you had the whole thing before?
Yeah.
Ah, sucks.
Yeah.
So that's what I explained about PSE channels, the importance of them. But basically what they say, like, oh, so we have 59 20 megahertz wide channels. Devices, remember the association process. Have we seen the association process yet? Maybe not. The association process, the devices have to scan for channels to discover networks. Go to channel 1, listen for beacons, go to channel 6, listen for beacons. They say, like, and now with all these channels, they're going to go to channel 1 and 5 and 9 and 13 and 17 and 21. It's like going through all those 59 channels looking for networks. It's going to drain the battery of a device looking for networks in all these 59 channels. So he said, well, let's just create some that's where you're going to look for the PSE. So preferred scanning channels, that's a thing that you have to consider. And at the beginning, there were a lot of problems. They fixed many of those. Some tools like Ekahau could not see devices APs that were advertising in non-PSE channels. So if I, for instance, have access points in channels that are non-PSE, the tool Ekahau would not find them. So let me just see if I can bring up here something really quick. Let me open a file from last week. And where is my stuff? There we go. So if I open, let's say if I open, there we go. So let's open this guy. So that's 24, that's 5, that's 6. This is all 80 megahertz wide channels, okay? And notice that the primary is this red one. So these red ones is the same as these black ones. See the black ones out here? Those are the preferred scanning channels. And that is also the primary channel where the management and control frames go. So all of these guys are causing each other CCI, co-channel interference, because they're on the same channel, but they have the same primary. Let me see if I can find one that has 40s. Let's see. So all of these are 20 megahertz wide channels. See, there are some 40s in there, but this is trying to get 20s to work. And of course, many of those channels are going to land on a non-PSE. So here the PSE is 69, but then there's an AP here in channel 65, another one 61, another one in 57. Those are just 20 megahertz wide channels, okay? If we're using 40s, let's see if I have a 40. Oh, yeah. Let's see if I have. This is probably going to be 80s. Yeah, let me just open. I sort this out by date. And let's open. Oh, it's still in the 80s. Come on, let's see. See if I can find that one with 40 megahertz wide channels. That's an 80. All right. I'll show you one for the University of Utah later, but then the 6 gigahertz spectrum has become available, not everywhere. We have more channels, and then it is not harmonic. Make sure that in your regulatory domain or in the country where you're designing Wi-Fi, find out if it is available and if all of it or some of it is available. So this is a band comparison of 2.4, 5, and 6, if you have it available. This is just a rough picture of what channels are all about. This is Times Square. That's many years ago. I had a guy who said, like, yeah, we're going to put this open roaming stuff in New York, in Times Square. And I happened to have a survey of Times Square and said it, and I told them, like, really, where are you going to place APs in 2.4 in Times Square? It's already crowded. It's already congested. Where are you going to place them in 5 gig? 5 gig is already crowded. It's already congested in Times Square. So in this case, 2.4 and 5 is really congested spectrum. Using 6 gigahertz will open up more channels. So let me, before we leave this, tell you about the automatic frequency coordination. The way this is going to work, let me look for a slide that doesn't have too much in it, and then we'll write on it. How's that? Let's just create a new one. Here, let me come over here. Oh, actually, I'll do it right here. So let's say you have an access point. Let's say that access point is in 6 gigahertz. So originally they said you can use 6 gigahertz indoor, low power. So those are called low power indoor access points. In 6 gigahertz, you can use indoor access points in 6 gig, low power. Why? Because they don't want you screaming and yelling out there in the open, in a stadium, a parking lot, in an open space in 6 gig, really loud, because then you may interfere with these other entities that they are the incumbents. They are the ones that own, the ones that pay for that spectrum. So we say, okay, we'll let you use it indoors, quiet, no power. Okay. So, but 6 gig is really helpful in the stadiums, you know, like when we have lots of access points and lots of people. 6 gig is really useful there. So yeah, but that's outdoor. For outdoor, you need standard power. You need more power, and then you need to have a way to, because DFS works that each entity listens, and if there are radar signals, I'll just move, okay? But then they say, can we do that for 6 gig? Like, no, there has to be an entity that regulates this because there is licensed spectrum. So basically say, for you to use standard power, let me just, standard power. That looks dirty. Here, let's just put it in here. If you want to use standard power, then you're going to need automatic frequency coordination. In reality, it's not that automatic. It's kind of automatic, but it's not like you do it yourself. Here's how it works. You're going to have an AFC. That's an intermediate automatic frequency coordinator. It's a company, an entity that basically will work in between you and, let's say, the government's database of frequency. So that's going to be, I don't know, let's say the FCC. Okay, they have a list of the people that pay and buy to use licensed spectrum in certain areas. So if this access point is in 6 gig, let's say it goes to the Wi-Fi Alliance. The Wi-Fi Alliance happens to be one of those organizations that provide AFC services. You go to wi-fi.com, y-fi.com, that's the AFC. There are like, originally were like 13, I think there are like 7 entities. I think Broadcore, I think something federated. Man, there are 7 organizations. I don't remember any right now. Sony, I think they have AFC. Basically, I just say this, those are organizations that will be like the broker. Here's how it's going to work. The access point, if I'm going to use 6 gigahertz, let's say in this building, okay? Then the access point goes to the AFC service. It's like, hey, I want to use 6 gigahertz here. And it has to provide like GPS coordinates. It has to provide the altitude. How high is this guy? It has to provide the FCC ID number. It has to provide, I don't know, a whole bunch of other information. Okay. This is who I am, and I need 6 gigahertz in here. So the AFC is going to go to the government database and say, hey, Martin wants to use 6 gigahertz in this GPS location at this altitude. This is his ID, and here's some other information, serial number, I don't know, a whole bunch of stuff. And then the FCC is going to look at that GPS coordinate and say like, yeah, over there. Mauro pays for a point-to-point link that he has going to a substation, and then that spectrum in certain channels is being used. So tell Martin that he can use different channels and he can use these power settings. So now the AFC lets Martin know that, sure, Martin, you can use 6 gigahertz standard power in this building, but here are the channels and here's the power that you can use, okay? And do not do anything different than this, because this is what I'm authorizing you to use. Every 24 hours, Martin has to go back and check and make sure that those channels are still available and that he can use those. Now, what does that mean? That means that the access point has to have a GPS in it. And then, yeah, if you have an access point here by the window, it's going to get, you know, from the satellite, it's going to get GPS. Let's just use a different color. Let's just use a different color. The GPS signals to know its location. But how about the access points that are inside the building that don't have access to the GPS? Then in between these other access points, some companies like Extreme, they're using 802.11 MC. And that has to do with fine-tuning measurements. Did I spell that right? Fine. Is it fine timing? Oh, man. Another acronym we have to memorize. Hey, Martin, or somebody, look that up. 802.11 MC. What does FTM stand for? Is it fine-tuning or fine-timing measurements? Look it up. Let me know what that means. Then that's basically a technology that is for ranging, and then it's going to know that this access point is this far or that far from this other access point, and it basically on a map builds all of the access points that are in the location, okay? So that they are going to be using Wi-Fi standard power, either indoor or outdoor. So indoor is more difficult because now the APs, not all of them have GPS access. Maybe they have a GPS unit, but they're inside the building. They don't have access to the radar. So the one that is in here is going to be called an anchor access point that has GPS access. Now with those GPS access and ranging to the other APs, is going to find, what is it? Anybody find it? Fine timing measurement. Yeah, I was right. Of course, I'm never wrong, except when I'm wrong, which is most of the time. So don't believe everything I say. Key aspects includes meter accuracy, round trip time, calculation. Okay, thanks, Martin. So FTM, fine timing measurements. And it's basically trying to identify where the other access points are to let the AFC know, yeah, I have these other APs and we are in these locations. Then let us know which channels to use and what power settings to use and then it has to constantly do it. Now, if you're at a stadium and then the stadium has open seating and all the APs have access to a satellite, then that's good. But that, in a nutshell, is what AFC is all about. It's here in the US and Canada. Other regulatory domains, probably they haven't implemented this quite yet. I don't know if they're going to call it the same thing, AFC, but automatic frequency coordination, that's what this is. All right, questions or comments up to this point? Ooh, where did this thing go? Well, I think this is where we end our session today. For the next class, we're going to talk about association. What's the next class? I don't know. So AFC can tell the AP to reduce power and change channel? Yes, Simon, it absolutely does. That's their job, actually. And the APs have to obey the AFC rules. Again, there are different companies. Let's see if we can now, we have a few minutes, look up, I don't know, AFC providers. USA. Adult foster care. Yeah, no, that's not what I'm looking for. Automatic frequency coordinators. Coordination providers USA. Automated frequency coordination providers. Okay, here we go. Broadcom, ComSurge, Federated Wireless. That's the one I was thinking of. Qualcomm, Sony, the Wi-Fi Alliance, and the Wireless Broadband Alliance, alongside subsequently approved operators like Axon Networks. So that's how many? 1, 2, 3, 4, 5, 6, 7. Here we go. So that's what those guys do. Now, the question's been like, who pays for it? Because somebody's got to pay these guys for providing that service. So I think most vendors have said, like, you know what, we'll just pay for that one, buy our equipment, and we'll make sure we come to agreement with the Wi-Fi Alliance or whomever in order to give you access to AFC without you having to set up an account and paying them and doing the whole stuff. We'll do it for you. But now they have to provide those. So let's see which AP vendors with standard power 6 gigahertz. Cisco, Progress, Juniper access points, FCC approved, Juniper series of high performance access points. So now when you see 6 gigahertz, see if they are AFC or standard power or LPI, low power indoor, and all the vendors are going to have different models, like some that only work indoors, some that only work with standard power, and then you have to have AFC, and then you have to have GPS, and then you have to have all of the requirements. Maybe not all the APs have GPS, but then you're going to have some anchor APs that have GPS, and then they provide fine timing measurements metrics to identify the location of the other access points in your organization. So AFC is a thing, and there's a whole bunch. Mr. Parsons has been publishing. Let's see, LinkedIn, not Link Live. Let's see, LinkedIn. Oh, not here. Let's open it in here. Let's see if Keith Parsons. He's posted lately, he had some postings about AFC. Oh, this one is one of them. About 6 GHz LPI versus standard power. There's restrictions on channels and the power you can use per channel. And I have to study this myself because there is a lot of stuff related to this power and the amounts of power that can be used. And if you're using 20s or 40s or 80s, then you lose power, you gain power. Clients on LPE have to be 6 dB lower than the access points. If you go to standard power, clients gain those 6 dB, but only in certain channel widths. It gets complicated. So my recommendation is, if you're watching this video about 6 GHz and about channels, 6 GHz is not as simple as, hey, turn it on, I have a 6 gig AP, blast it everywhere. No. Doesn't quite work that way. So study it. Channels in Wi-Fi, this is how it works. That's what we have covered today. Let me bring my other device. Where is it? Right here. And bring this guy up. Today, we have been talking about channels. Okay, 2.4, 5 gig, 6 gig. We've talked about 20 megahertz wide channels and 40 megahertz wide channels and 80 megahertz wide channels and 160 megahertz wide channels. And yes, I know for marketing purposes, people talk about 320. Yeah, it's not going to happen in real life in enterprise environments. There's just not enough spectrum. So yes, numbers look good, but there are a lot of other losses that you go through because you're not going to have as many. Ned, first generation Wi-Fi 7 indoor APs didn't support GPS in general. Okay. And Wi-Fi 7, people assume that Wi-Fi 7 is automatically a 6 gig AP. Most of the APs we've dealt with, Wi-Fi 7, they're just 2.4 and 5 gig. Wi-Fi 7 is just another technology. We'll talk about it in a different session. But yes, Wi-Fi 7 does not necessarily mean you're going to be doing 6 gigahertz. You'll be doing 802.11ax, Wi-Fi 6, but not necessarily in 6 gigahertz. So that's another thing. If you're buying APs, make sure that the APs have 6 gig if you need 6 gig, because getting Wi-Fi 7 does not mean that you will get a 6 gigahertz radio in your access point. You know, one of the Wi-Fi 7 access points that I like a lot, let me bring you one. Are these guys, the Ingenious. Yeah, let me stop sharing here for a second. So this is an Ingenious AP. This is a Wi-Fi 7 access point. This is the Cloud 7. Two is a ECW. Oh, my glasses. In my eyes. ECW 520. ECW 520. Okay. This guy it has 3 radios, 2.4, 5, and 6 gigahertz. Really easy to configure. We use this in WLPC in Mexico for testing and learning about Wi-Fi 7. Wi-Fi 7 is really cool if you have the right equipment, the right APs, the right clients. So, and it does have 6 gig radios. So with this, my dear friends, we come to the end of this session 356 of Tesos and Wi-Fi. Today, this part of the class, the free Wi-Fi design class from Wireless LAN Professionals, we brought to you this session to cover channels. We talk about channels, channel widths, the bands 2, 4, 5, and 6 that we use. CCI, co-channel interference. We talk about adjacent channel interference, about overlapping. Sebastian asked, which vendor does Ingenious compete with? Well, with all of them, I guess, but at that price range, because they have like no monthly or subscription fees, it's free. So it's like Cambium. Also Ubiquity. Ubiquity has a lot of Wi-Fi 7 access points. We in Valencia in Spain last year gave Ubiquity Wi-Fi 7 access points. Those were just 2.4 and 5 gig, but they were Wi-Fi 7. So ubiquity is in that range. Yes, Ned, that's right. Ubiquity and Ingenious and who else? At this price range, of course. Cambium, I'm sure Cambium has a Wi-Fi 7 AP. Let's see. Cambium Wi-Fi 7 AP. There we go. Let's see. 7 Wi-Fi 7 indoor enterprise wireless access point. Cambium networks AP designed to deliver cutting edge performance, flexibility. Here, let's just download the data sheet. So tri-band, see, this has 6 gig, 5 gig, and 2.4. Hey, this is like direct, similar to this guy. It's 2 by 2 by 2 on those guys. It's got 3 radios, 9.2, 2.5, low power indoor mode, see? Now it starts making more sense what low power is, what standard power is. Unbeatable value for the market. Can anybody look for the price? Oh, TP-Link has a Wi-Fi 8, Martin, and they have it out there?
I know you can involve yourself in a beta or something, and you can pre-order, and then
okay.
Like September, October, something like that. So it's not so far away.
Okay.
I have to go look. Yeah.
All right. So Wi-Fi 7, yes, it's going to be the same thing. It has a 2.4 radio, 5 gig radio, and 6 gig radio. Guess what about channels? It's the same thing. You're going to have 20s and 40s and 80s. And the channel we have to understand how channels are distributed, use what advantages or disadvantages we have of using one band over the other, and what channel widths. The wider the channel, the more bits, ones and zeros we can send, but then the more congestion we can have because we have less channels. So get familiar. If you're new to Wi-Fi, start learning about channels, okay? This is the end of session 356. Today is July 25th, 2026.
I have a comment for everyone. I didn't realize that when you do recording, Fenny, are you recording also the chats? So the chats will be there in most cases.
The chats will be uploaded and saved if we come to the Wi-Fi of things. See, like here we have chat notes. So the links and notes will be in there. So remember, if you just want to follow the Wi-Fi design class in English, then you can click here. You go to the Wi-Fi of things.com, click on WLANPros Wi-Fi design class. And then next, my friend's going to upload this video and add the notes for session 356. So they're not going to be in sequence like class 1, class 2, class 3. No, you're going to have to dig, but we're putting them together for you. So part of this class, this is it. Notice that, for instance, let's see if there are, see, like this one's got notes, some highlights. So any notes that we have, see chat notes, we're going to put them right there. Your notes and links and anything that we put, is going to be added in here for you to come and study. So has this link.
Sorry to interrupt you. That's actually super great, because a lot of webinars or something you have attended, people don't save the chats. So I didn't realize that in the chat box, if you find those 3 bullet items in the top right corner, you can always save the chat yourself as an attendee, which is super interesting if you're attending some webinar or something.
Oh, save chat. So if you open the chat, the 3 dots up above, it says save chat. And where did it save it? Showing file. Oh, it creates a file.
In the Zoom folder.
Yeah, it creates a text file with the chat. Yeah. So we'll clean it up a little bit, because then it's going to be too long on the session. But then maybe what I can do is just upload that file and then have that text file in there so that people can just download the whole thing.
Because what you really from your session is all the links to the thing you are showcasing us. But
no, on the other sessions, we just keep all the notes in there. Let me see if I have, like this one, if I go to this class, see, puntos claves del video, sesión. notes. Yeah, we'll keep those. So this is the one in Spanish. We started session 299 and we're further along the process, but in this one in English, we'll just keep recording and uploading stuff. So with this, my friends, we get to the end. Thank you very much. Have a very nice rest of the weekend. This is Wireless LAN Professional Wi-Fi Design class. You know, free love for everybody and free Wi-Fi training for everyone. Have a good one.
See you, Manchester.
See you in Manchester. Yes, that's coming up.
Thank you, Ferney. Thank you.
Hey, you're very welcome. Take care.
Yeah. Ciao.
Bye. Ciao.
Ciao, ciao.
Thank you, Ferney.
Ciao. Ahí nos vemos.
Gracias.
Ciao.